So the true strain can be given by this expression, and I can break this to Li plus delta L divided by Lf, which is equal to ln of, so this becomes, so this is I initial, so this becomes 1 plus delta L by initial length, and you know what it is. So this is engineering strain delta L by L, right? And in doing so, we have not assumed the volume to be constant in doing so. So this relation between strain and, so engineering strain and true strain should hold even for elastic deformation, right? So this is our relationship, 1 plus E, right? Okay, so now let us try to find out the relation between true stress and engineering stress. So true stress is defined by the load which is applied in the current form divided by the current area. Okay, so load divided by current area, right? So this we can call it, let's say, final area. So let's say we are calculating the stress in the final position. Okay, so then we can write this as load divided by area of, so let's call this initial area into initial area by final area, and we know that this part is engineering stress. Okay, so engineering stress takes the initial area and load of the current value. Okay, so now this becomes what? This becomes, so let me denote engineering stress by the symbol S. Okay, so this becomes S into AI by AF. Okay, and now we will be taking the assumption of constant volume. Okay, so AI by AF can be broken into S into LF by LI. If we assume constant volume, so area initial into length initial is equal to area final into length final, so we change that to that, and then again now we can break it like that. So LF will be Li plus delta L divided by Li, so this becomes equal to S into 1 plus E. Okay, so remember that we did not assume constant volume condition, was not assumed for finding this relationship, but here we have applied. So this relationship is only valid in plastic deformation, but this is also a vague term, so I have to tell you that this is only valid in plastic deformation as long as volume is constant. So in plastic deformation you can have a condition where volume is not constant. In some of the materials, even in elastic deformation, even in plastic deformation, usual plastic deformation, no. So in polymers you have sometimes volume is not constant, but polymer is a different type of material, and there usually we have either viscoelastic, viscoplastic, or non-linear elastic deformation. Okay, so that's a different case. So the important point here is that constant volume, this relationship is valid only when there is constant volume, and in plastic deformation as long as there is no damage. Okay, as long as that does not happen, then this relationship will hold good. Okay, so now what happens when we test that material? So you remember that specimen we put. So another question which can be answered also at a later point of time, but now I have told you, so we can address that question even now. And so the dog bone sample, or maybe you will understand the answer for this question. Let me just erase the question here and we'll come back to the answer when we are more ready to answer this part. So the question is, why the design of tensile sample is such? Why instead of just putting this cylindrical bar in the machine, why do we make such kind of design to test the tensile properties? So we will come to this question later. Now what we should understand is that when we test this kind of specimen or the flat specimen, so we have another design which we drew in the last page. So it looks like this. So you can either clamp it or you can have a pinhole. Okay, and in this case you can have thread. Okay, so when we test such kind of sample from the machine, we usually measure using the load cell. We usually measure the force. Okay, so we measure the force and we measure the elongation. So we measure so what you actually can measure, one possibility is that you put the strain gauge here and here. So it's a kind of gauge which measures the distance between these 2 points, or you can calculate or you can measure, the machine can measure the amount by which the upper frame, if you remember. So this was in a very simple way, if this is my sample fixed in the fixture and this fixture is being pulled up, right? So this part is fixed and this part is being pulled up. So what this machine can calculate or measure, that how much it is moving up. Okay, so you can have this elongation, so final length, you can have final length, or you can have strain directly. That can be done, but that will be engineering strain, and the force will be measured. Okay, so initially for metallic materials it will be a straight line and then the load will be increasing non-linearly, then it will become very constant and then it will start decreasing. Okay, and then after a certain point of time it will just break, and as soon as it breaks the load will drop to 0. Okay, so you will have final point here. Okay, and then you will have to stop the machine, or if it is a very sophisticated machine it will stop. There are 2 ways you can do this testing. One is displacement controlled mode. Displacement controlled mode or force controlled. Okay, There are other things involved with the testing which we will understand. So we will talk about these two different modes of testing the machine. We will also talk about machine compliance when we really talk about the experimental part of it. But right now we are talking about the theoretical part of tensile testing. So we will get this data, we'll get force versus displacement. Okay, so displacement between these 2 points. So that can be resembled either by delta, like this symbol or this symbol, and it can have a unit of millimeters, and the force can have a unit of Newton or kilonewton depending upon the material. So if you are testing a metallic material, usually steels, then this force will go in the range of kilonewton, again depending upon the size of the specimen. If you are testing polymers, then the force can go in the range of Newton. If you are testing biomaterials, the force can only be in the range of millinewton, sometimes, yeah, in that range. Okay, so it depends on the size of the specimen, and it depends upon the material. Okay, so now from force and displacement you can draw or you can calculate, and this can be done also digitally, either by the machine itself or the software in the machine, or you can do it by just exporting the data from the machine. So you can get from the machine the force and displacement values and the post processing. So the further analysis you can do by yourself. So you have the values of forces, and so you also have measured before testing the initial area of the specimen and the initial gauge length of this specimen. So before testing, what you did is you calculated the initial area A0 and you calculated the initial length L0. Okay, so now you have force value. So if you divide force by this, you get the engineering stress. So we have denoted that with S, but we will come back to sigma. Don't get confused, I will write ENGG in the subscript so that we are very sure that this is engineering stress we are talking about. And this we will get by dividing all the, so Fi I am writing, where I will change depending upon the number of values you are getting from the machine. So all the force values you can divide it by the initial area, and you will get the values of engineering stresses. Similarly, you will get the value of engineering. So yeah, so that I will also write ENGG. So engineering strain, which you can get as, so you have all the values of displacement, different displacements, right? So if those values are actually the final length at different time frame, okay, during the process of testing, then you will have to calculate first delta L. Okay, so let me explain that part. So what happens while testing is that there are 3 values you will be getting. The first value will be the time. So once you start the test, you say I started the test at 0 seconds. Okay, and when you started the test, just to be sure, and we will discuss this again in the tensile testing part, you apply a little bit of force there. You don't start with a 0 force. So but you apply a force which is here somewhere, so you are sure that you are not deforming the material to a very high strain value. Okay, so let's say you applied 1 kilonewton on a steel specimen. So for a steel specimen of significant diameter, this amount of force is insignificant, right? So you applied this much amount of force and your displacement was 0. Okay, so you started with 0 displacement. Okay, so this is how you started. Now depending upon the rate of data acquisition, let's say after 5 seconds the machine records that the load has increased to 2 kilonewton, and the displacement is 0.1 millimeter. Okay, similarly at 10 seconds you have 2.5 kilonewton and the load has increased to 0.2 mm. So this is how you get the data from the machine. What you do is you divide all these values with the initial area equal to F divided by A naught, right? So you will be getting all the values here by dividing whatever is the value of A naught, and then you can get the engineering strain value by dividing this delta, and you see this is actually delta L values, right? So you can divide the value of displacement with the initial gauge length. Okay, and so initial gauge length was L naught, so this will be your stress and strain values, right? And then let us go to the next page. So then what happens is you have now calculated stress and strain value, right? And you can plot that, and usually for most of the metallic materials, so this axis is strain axis engineering and this is my stress engineering. Okay, so this will be in megapascals. So assuming that I have tested steel sample and strain has no units, so this will be unitless. Okay, so this is engineering strain. So this graph will look something like this. So initially, and we'll talk about the different aspects of it, and then it will start non-linear and it will increase and then it will decrease and then it will fail. So at this point of time it failed, the specimen broke into two and the test stopped. Okay, so now there are different points in it. First one, where, so initially what is there? Initially the region where sigma follows a constant relationship which is given by elastic modulus into the strain. Okay, so this part is the linear part, right? This part is the linear elastic part. Okay, which stops here. That point is not clear where it stops, but let's assume that it stops somewhere here, and then non-linearity starts, right? So this point should be called the starting of non-linearity. So this point is called proportional limit. Okay, proportional limit, which is many times equal to the yield point. Okay, yield point is the point where plastic deformation starts in metallic materials, right? So this point is proportional limit, also known as yield point in most cases. Okay, so the value of stress here is called the yield stress, which is denoted by sigma with a subscript of naught. In some textbooks or literature you can find sigma ys written. Okay, but usually this is the symbol which is used for yield strength or yield stress. Okay, so this is that, and then stress increases and then it reaches a maximum value. Okay, so this is the maximum value of stress, which is called the ultimate tensile strength. UTS, also called tensile strength, just tensile strength. Okay, then what happens, that stress starts decreasing. The question is why it starts decreasing. We will come to that question. But it starts decreasing, and it decreases only when you plot engineering stress versus engineering strain plot. And then it reaches a value which is the minimum value, so to say. And this minimum value can actually be higher than yield strength also. So it can break somewhere here also, right? So it will start decreasing, and then there will be a final value of stress at which the specimen breaks into two, and this part, so this part is called sigma f, or failure strength of material. Okay, so corresponding to this point, you will have failure strain. Corresponding to this point, you have uniform strain. Okay, now there is something interesting here, for which I will have to draw it again. There are actually many things in this plot. So this is our linear part, and then it starts to change in non-linear behavior, right? And then it goes there. Now what happens if I unload it somewhere? So now this part is very important. If I unload it here, okay, if I unload at this point, so let's call this point A, okay, and then if I unload it at this point, let's call this B. So what will happen is that this is how I load it till A, right? And when I slowly remove the load, and I have to do it slowly, okay? So there should not be any effect of temperature. So this has to be isothermal, okay? So when I unload it, the strain will decrease and it will go back to its initial position as the stress will decrease to 0, okay? So it will go back following the same path, resulting in no net deformation, okay? So this is completely elastic, right? But what happens when you unload it from here? So when you unload it from point B, then it will not go back like that, okay? Instead, with decreasing stress, it will come back here, right? Okay, so at this point of time, you had total strain which was equal to epsilon B, which is the strain at point B, right? Now when you started unloading, it recovered with this much amount of strain, right? So this much amount of strain disappeared from the specimen, and there is no trick here. There is no temperature dependence, or I didn't do it fast. I did it with the same rate. But even then, only this much amount of strain will come back, and this much amount of strain will not recover. So this is irreversible amount of strain, right? So material is permanently deformed by this much amount of strain, and this is the plastic part of that epsilon B here, and this part is the elastic part. So epsilon B, the total strain, has a contribution from elastic deformation plus plastic deformation, and this part will recover when you unload it, and this part will not recover after unloading. Okay, there is another interesting thing. So while unloading, so the slope here is denoted as E, which is modulus of elasticity, right? Because here in the linear part, the stress and strain follow this relationship, which is generalized Hooke's law. And so I think there is E also here. So yeah, so I think there was an E. So Hooke's law is comes from Robert Hooke, who was I think he was the chairman of Royal Society before Isaac Newton. And yeah, there is an interesting story there. So as long as Hooke was there in the Royal Society, he did not allow Newton to even come in or get entertained in Royal Society. And when he died, only then Isaac Newton could go there, and then Isaac Newton became the chairman of the Royal Society. So that is generalized Hooke's law, and the slope of this linear part is called the elastic modulus. So when you unload it here, it will have the same slope. So again, it will follow the same slope, right? So although we are not going to study that part here, but because I am explaining this, so I should also tell you that after crossing this ultimate tensile strength part, if you unload it from this point or this point, so let's call that C and D, right? If you unload it from this point, you will have similar phenomena of elastic and plastic deformation. So strain which will recover and strain which will not recover, but there will be a difference, and that difference will be that this slope will change. So here it will not be E, and when you do it from this point, the slope will change further, okay, and you see that slope is decreasing, okay. So we will try to understand the reason behind what is happening at point C and D when we unload at a later point of time, okay. When we talk about damage, then we will discuss that part. So now you know that there is elastic strain, there is plastic strain there, and this is the proportionality limit, and after this plastic deformation starts, right? And this is the usual stress strain curve for most metallic materials. What will be the so this is my sigma f failure stress, right? What will be the area under this curve? So the area under this curve will be integration. So you can take strain from 0 to failure strain sigma into d epsilon, and this will be the strain. It's called a strain energy density. So strain energy density, because this integration is actually energy per unit volume. It has the dimension of energy per unit volume. So that's why it's per unit volume, so it is called density, the density of the energy, okay. So the amount of energy which is consumed until failure defines the toughness of the material, okay. So the toughness of the material, right? And this toughness is different from other definitions of toughness. So this is one type of toughness which can be calculated, and we call this tensile toughness. Okay. So when we do this testing, we can get a lot of information. So what we get, what are the properties which we get? We get the yield strength, we get the ultimate tensile strength, we get the uniform strain, we get failure strain, we get failure stress, right? And we get toughness. So we get all this from one single experiment. Okay, we can also calculate elastic modulus to certain extent of accuracy. Okay, so we can get this also. So from one single experiment we get too many information about the material. Okay.